Welcome back, everyone. This is Lesson 2 of our Momentum series. I'm Beanish, and today we're going deeper. We'll explore how momentum behaves in different types of collisions, how it connects to kinetic energy, and how Newton's laws tie into all of it. Let's go. By the end of this lesson, you'll be able to clearly distinguish between elastic and inelastic collisions, relate kinetic energy and momentum through an important formula, and connect all three of Newton's laws to real-life examples involving momentum. Let's break it all down. First up, elastic versus inelastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. That means the objects bounce off each other with no loss of total kinetic energy. In an inelastic collision, momentum is still conserved, and so is total energy. But some kinetic energy is lost, usually transformed into heat, sound, or deformation. Most real-life collisions lie somewhere in between, never perfectly one or the other. Let's visualize this. Imagine two balls colliding. In an elastic collision, they bounce away cleanly. In an inelastic one, they might stick together or deform slightly. Motion diagrams or simple animations are great for illustrating these outcomes. You may be asked in exams to classify a given collision as either elastic or inelastic. Analyze the three situations shown here and suggest whether they are elastic or inelastic, and why. Now here's a key relationship. You already know Ke equals 1/2 mv squared. Since momentum P equals m times v, we can rearrange and get Ke rs p squared over 2 minor. This is super useful when solving problems where mass and momentum are known, but velocity isn't. Also remember, kinetic energy is a scalar, so direction doesn't matter here. Let's revisit Newton's laws, this time through the lens of momentum. Newton's first law says, momentum of an object stays constant unless it is acted upon by an external force. The second law becomes, force experienced by an object equals the rate of change of its momentum. And the third law? It means when two objects interact, they experience equal and opposite forces or changes in momentum. Now apply Newton's third law to real life. Imagine two cars collide, a heavy SUV and a small hatchback. They exert equal and opposite forces on each other and thus have equal rate of change of momentum. But the lighter car has less mass, so it undergoes a bigger velocity change, which is why lighter vehicles often suffer more visible damage in crashes. It's momentum transfer in action. Quick recap. Elastic collisions conserve both momentum and kinetic energy. Inelastic ones conserve momentum, but not kinetic energy. And Newton's three laws all tie beautifully into momentum, from inertia and force to equal and opposite change in momentum. Keep practicing problems and relate these ideas to the world around you. They're everywhere. See you in the next lesson.